Good afternoon. My name is Ravinder, and I welcome you all to the fifth episode of this series. For today's science story episode, our guest speakers are Dr. Ambily Suresh and A.G. Sreejith. Good afternoon. My name is Ravinder, and I welcome you all to the fifth episode of this series. For today's science story episode, our guest speakers are They both belong to the southern state of Kerala. Both have joined for MTech program and subsequently did their PhD with Professor Jayant Murthy. They were deeply involved in IIS balloon program from beginning and developed various astronomy instruments for UV observations from space. Ambli's PhD was on development of detectors for space mission and balloon flights. She developed photon counting units for space applications and also designed and built balloon-borne NUV imager and spectrograph. Ambily is now a research scientist at University of Colorado, Boulder, USA. She is currently working on instruments and new technology for ultraviolet observations from space. Sreejith has completed his PhD in 2017 on studies of Earth's atmosphere from space and near space. He worked on high altitude balloon experiments and developed altitude sensor, pointing system, and photon counting unit for CubeSat payloads. He also carried out air glow studies from fused observations, analysis of diffused FUV data from New Horizon, trace gas mapping with high altitude balloons, and conducted spectroscopic observations of comet Izon. Sreejith is now working as a postdoctoral fellow at Space Research Institute, Graz, Austria. His research work focuses on characterizing exoplanet atmosphere and building instruments for observing them. While the search for Earth-like planet is still on, both Ambily and Sreejith feel strongly about keeping this planet safe and habitable for future generations. They are also united in the common goal of promoting and building a just and equitable society. Please join me in welcoming Ambily and Suresh. Ambily is joining us from Colorado, US, and Sreejith from Graz, Austria. Welcome, Ambily and Suresh, and thank you for accepting our invitation. So as per our format, we will play a pre-recorded video of your science story. After that, we will have some time for discussions and question answer sessions. Audience can post their questions and queries in the comment section below. So now I'm going to play the video. Please mute your video and also the audio.
Hello everyone, my name is Ambily. I'm a research scientist at the Laboratory for Atmospheric and Space Physics, part of University of Colorado in Boulder. I finished my PhD from IAA in 2019 and then joined here in the summer of 2019.
Hi, I'm Sreejith. I'm a postdoctoral fellow at the Space Research Institute of the Austrian Academy of Sciences in Graz, Austria. I also did my PhD from the Institute of Astrophysics. I finished my PhD in 2017 and have been working in Graz since then. Ambily, continue.
So I guess we'll start with some background on how we ended up where we are now. So I grew up in a village near central Kerala, near Thrissur, and I did most of my schooling there. And growing up, I'm not sure when exactly or how I got interested in science, but I guess there are a lot of factors, and that includes my teachers and family, and especially my parents, who are like really chilled out and open-minded and pretty much let my brother and me do whatever we wanted, which I guess was quite a privilege. And I'm also thankful for my teachers in school for instilling all the important life lessons and values in me, and also like they somehow believed me when I said I wanted to be a scientist, and let me participate in all the quizzes and science fairs or pretty much anything to do with science. And I was also fortunate to have access to a lot of books. That's something my parents didn't mind spending money on. And being lazy and being really bad at sports, I spend a lot of time reading. And the reason mostly why I got interested in popular science books is due to an organization called the Kerala Shastra Sahitya Parishad. They were interested in like science popularization among children and even adults. And they had a lot of magazines published, and two of them are called Eureka and Shastra Keralam, which are intended for like primary and high school students. And there used to be a lot of articles on scientific principles and even current affairs, all in a manner easy to understand for kids. So that was a huge factor in getting me interested in science, and even astronomy, because they used to have this monthly sky chart and some description of any interesting astronomical phenomena that is happening that month. So I remember we used to have half an hour of power cuts every night, and my brother and I used to sit outside and look up at the sky, trying to identify what is there in the star chart. And I also remember they used to tackle a lot of superstitions. There was like a solar eclipse in 1995 or something, and there used to be a lot of articles and activities described in Eureka, trying to get people understand that it's not a big deal and what is actually happening astronomically. So I think those things definitely helped to raise the curiosity and instill a sort of scientific temper in me, and I'm sure on many other kids of that generation. And the other thing was that we used to watch this ISRO launches that used to be telecast on Doordarshan, all of us, and that also definitely helped me get interested in space. Later, when I was in high school or something, there was also this program for gifted children that was like an exam conducted by the government for all the school children in Kerala, and those who were selected used to have this bi-monthly classes on like a wide variety of topics, like ranging from like fingerprint recognition to genetic engineering, all conducted by people who are like actually working or researching in that field, and also many of them were women. So that was definitely a reason that made me believe that I can be a scientist also, and I should definitely thank the organizers and people who conducted those classes, and also my mom, who used to take me to these classes like many times.
So I have similar stories as Ambily from my childhood as well. I was born in an adjacent district to Ambily. In Ernakulam, I was born in a small village, and I attended school at Habitable school. I would say that my mother and my school played an important role in introducing the interest in astronomy. My mom was a school teacher and would always show us experiments related to the science concepts that I learned in school. So I still remember her showing stuff like how a seed germinates and you get a small sapling out of it, how water is absorbed through stem of small plants, etc. She was also interested in looking into newspapers and magazines and finding what are the and my brother do watch these astronomical events. Like I remember trying to watch few of the meteor strikes that were happening, maybe one of the comets as well. So as Ambily said, Eureka also played an important role for my interest in science. I guess it did for a lot of young people of our age from Kerala, because Eureka was one of, like, it was written in such a language that you could easily understand, and also they would always convey like they were mostly up to date with the current standings of the science. Like now I look back to the current versions of Eureka and find that, oh my god, like I can still learn things from Eureka. That is quite something. Like I also remember that the accident that happened with Kalpana Chawla happened when I was in my high school, and that actually had a deep impact on me. And I actually I wanted to follow her up doing astronomy in the future. But I wasn't a bright student like Ambily. Like I would like I kind of like progressed as I grew. Like I was I still make spelling mistakes. Like I can't spell words properly even now. I'm like really thankful for the technology that lets you do autocorrect in your documents and correct for most of your spellings. But I was a quizzer and I was really curious about stuff. I was curious about everything. And my mom was also like, she pushed us into reading when I was really small, and it slowly became an habit. And I would say that was an important part in me being curious as well as interested in sciences and especially astronomy. I was also an extremely sickly kid. My parents used to take me to hospitals or doctors every other week. So, but my mom did stick with me and taught me stuff that I would miss in school. I also had good friends who would sometimes complete my notebooks because I was sick, and like I should be thankful to all these people for where I am now. Ambily?
So, coming to how we ended up actually studying astronomy and coming to IA. So, in spite of all the interest, when I finished school, I had no idea how to actually become an astronomer, and I was not really good at using the internet then, and it was fairly new also. But somehow I had figured out that you cannot do a bachelor's in astronomy in India. There are not many courses for that. So I figured that I'll have to do physics. But I was not really sure about that. So I also wrote an engineering entrance exam and got a decent enough mark. So I was really confused. But in the end, like being a natural coward, I took up engineering thinking that if I don't end up becoming an astronomer, at least I'll have a job. So I studied engineering for 4 years in Cochin and like made a lot of my best friends and learned a lot about life and a little bit about electronics and communication. But in the end, after 4 years of engineering also, I was not sure how to switch fields and become an astronomer, and I was also not sure about studying more electronics. So I ended up taking a job in Bangalore in an electronics company. So again, I learned some little bit about VLSI and chips, etc. But more importantly, about like how to be professional, how to work as part of a team, and like how to be on time with things. So all those things I'm really grateful for. So after 2 years of working, I was really not sure about the whole astronomy thing then, because I didn't know the requisite amount of physics to qualify for any entrance exams in India, and I was not really sure about applying for PhDs abroad also. And so it was at that time that one of my friend's mom saw about this course in IA, which takes engineering students and lets them do an integrated MTech PhD program in IA, and I thought this will be really nice. And also I was living really close to IA at that time. So anyway, I wrote the IA entrance test at that time and got selected for the interview. And during the interview, I remember one of the interviewers asking whether I like regret leaving the job and joining IA and like not making as much money. So like in hindsight, to whoever asked that question, definitely not, no regrets, and particularly because I met Sreejith in IA.
So coming to me, I wanted to do I wanted to do physics after my schooling, but I had not so decent ranks as Ambily, but decent ranks enough, and the general society pressure pushed me into engineering. But I don't regret it now though, as because I learned a lot of things that helped me in the future from my engineering courses. But because I wanted to do astronomy, I used to constantly check the websites of all the institutes in India, like Indian Institute of Astrophysics, Indian University Center for Astronomy and Astrophysics, Raman Research Institute, etc., about their courses. And like I used to notice that most of them were for you would have to have some physics background. So my idea was that after engineering, I would go and do physics somewhere or something like that. but I guess it was during my third year or something that one of my cousins pointed me towards a newspaper advertisement about the MTech program in IEA. So I decided to take it during my final years, and I was selected for the interview. Like actually, me going to the interview and getting selected to IEA is a story for a day itself. Uh, so like I finally got the date for my interview, and it turned out it was between my final year university exam. So like I had university exams on the previous day and the day after my interview, and I thought, okay, I am not going to make it. But like my family and my relatives pitched in, and I was able to get flight connections to travel on the short duration. And so it was indeed extremely strange because that was my first experience of flight travel, like my air travel experience. That was my big city experience because like I agree that Cochin is not such a big city compared to Bangalore, and a research institute interview, the final exams of your 4-year college course. So everything happened in a span of 3 days. But I would like to point out that the admin staff in IEA were really kind, and they rescheduled my interview to an earlier time of the day so that I could catch my late flight so that I would reach for my exam the next day. So, but I think, like, I don't know why, but I was selected to the IEA, and it went well after that.
So coming to our PhD experiences, it was like a really unique and challenging and exciting time. So what our course does is, so it takes engineering students from various streams like electrical, electronics, computer science, mechanical, and it sends all of us to Calcutta for 1 year of coursework at the Department of Applied Optics and Photonics. And so I had some really great batchmates and a great time in Calcutta. And I was initially not very keen on studying optics, but somehow people at the department were extremely knowledgeable and very dedicated. So that really encouraged me to study optics and got me interested in the labs and projects and stuff like that. And so after 1 year of coursework, we also do some projects at the different field stations in IEA, some internships. And that also really helped us understand how these telescopes and observatories and the instruments in them actually work. And we also got an opportunity to do, like, develop small instruments for these observatories, and that was also a really good hands-on experience. And then after like 1.5 years of generic stuff, we had to select our master's project, which could possibly be extended for PhD as well. So, and for both masters and PhD, I worked as part of the high altitude balloon group in IEA with Professor Jayant Murthy.
So I don't have nothing else to add to the MTech years, like because it followed exactly how Ambily described. But it was, to another point to note, was that it was my first experience in a hostel environment as well. But I would also like to emphasize that the people we had teaching us about optics and even other topics of astronomy were really good. So we did learn a lot during this period. And after my for my project, I joined Professor Jayant Murthy, with whom I continued for my PhD as well. So it was really strange because, like, I think I was the first student coming from the MTech background who joined with Professor Jayant, and like I was happy that there was I had enough juniors and other students who joined after me, and when I left, the group was almost from one student, it had grown to 5 or 6 students, and I'm really thankful for Professor Jayant for us. He was a really good guide for us in many ways.
So coming to what we actually did for PhD, if you're based somewhere around Bangalore, you might have seen us as part of the outreach activities at IAA or IAC or something. But anyway, as the name suggests, we flew high altitude balloons. But why? So the reason was we were interested in something called the ultraviolet radiation. And you might also know what a spectrum is. So it is basically the different colors in light. So as you know, sunlight has various colors which are scientifically called wavelengths. And You might also know that the light that we actually see, that's called the visible light or optical wavelengths, that is only a small part of the broader electromagnetic radiation, which consists from like longer wavelength radio waves to shorter wavelength gamma rays. And what distinguishes these different wavelengths is actually the amount of energy that is contained in one discrete packet of that radiation, that's called photons. So that's about it. And even though we cannot actually see other radiation with our eyes, there are other instruments that let us record this light, that is like take pictures in these different wavelengths, kind of similar to how we take X-rays.
Yeah, or similar to night vision goggles that you have, that let you see that is basically in an infrared wavelength. So that's why it operates in infrared wavelength. That's why you can. Or if you have noticed that the CCTVs, most of CCTVs have IR LEDs on them, and that's why you are able to see images in the dark as well.
Yeah, and so coming to why we are interested in studying this different wavelengths, why don't we just take pictures in what we can actually see, the optical radiation? But the reason is that so each of these celestial objects emits radiation in various wavelengths, from like again radio to gamma rays, and the amount of radiation in each of these bands can tell you a lot about the physical property of that particular object. So for example, the temperature of the object determines how much radiation you get in different bands, and what elements are contained. The physical the composition of that element, that object also determines the type of radiation you get. So to study all these things, we need to have an access to these different windows of different wavelengths. But unfortunately, and especially for ultraviolet, so you know that sun has a particular temperature, and that is the reason we, in the case of sun, the maximum radiation we get happens to be in the optical wavelength that we can actually see. But there are some young hot stars which might have most of the radiation in ultraviolet. So, and there are many other objects that are like really interesting in the ultraviolet radiation. But unfortunately, you might also know that there is an atmosphere to the Earth, and it doesn't let most of the radiation come into the Earth. So as you can see in this picture, even though we have this large variety of wavelengths in the electromagnetic spectrum, there are only like really small portions of it that actually reach the Earth. So if you want to take a picture of sun or any star from the Earth, we can only do that from the Earth in these two bands, the radio and the optical band. And to get access to any other set of radiation, we have to go above the atmosphere, and that's space. And so to go to space, especially in the case of ultraviolet radiation, the main reason why it doesn't reach the Earth is the ozone layer, which is about at a height of 30 kilometers. And as you go higher, the amount of absorbing material in the atmosphere comes down, so you get access to a wider and wider window of the ultraviolet. So there are different ways to go above this ozone layer, and as you can see in this picture, we have shown multiple of them. So the first one that you see is called sounding rockets. So it's basically a rocket that carries your telescope to a height of about like 200 kilometers, and so it's a very short observation. You can observe for like 10 minutes, and then the whole rocket and the telescope and all the other electronics comes down. So those are called sounding rockets. And the other one you see here is called space telescope. So this is the Hubble Space Telescope that orbits the Earth at a height of about 500 kilometers. And it has a wide variety of instruments in a wide variety of wavelengths, and that includes the ultraviolet as well. And this one that you see here is a high altitude balloon. And
so, so high altitude balloons are kind of, so you basically know that hydrogen or helium gas is lighter than our atmospheric gases. It's basically because our atmosphere have mostly nitrogen and oxygen. So hydrogen and helium being lighter would naturally rise up into the atmosphere, similar to the normal hydrogen balloons you get from parks and stuff. So the basic principle of high altitude balloons are the same. So you have big balloons, not the small ones, which are filled with hydrogen or helium, like depending upon the availability and regularity. Like helium is much more rarer, and it has much more, it has more scientific, hydrogen also has scientific application, but helium being rarer is like really difficult to find. So depending upon the gas, like you may have hydrogen or helium, and the balloons are filled, and you attach a recovery system using parachutes, and then you have the payload what you want from which you want to do a scientific experiment, and you send it up into space. So depending upon the type of balloon, they can go anywhere between 30 to 50 kilometers. And there are balloons that just go, pop, and then come down, or there are balloons that would go to a particular height and float there for some time. So there are different type of balloons based on what you want to do. And once you are at this altitude, you will start your observation from your payload. And then once you have collected your data, you will bring your payload down back. So you would have some termination mechanism which would cut your balloon and the payload off, so that your payload will come down with a parachute and land. So the basic the project that we did included, we would launch the balloon, we would track the balloon on the ground with, we would have some form of communication with the balloon, radio signals that would be sending back. And once it lands somewhere, we go and collect it. So I would say that I was involved in the starting of the balloon group at IEA. So Professor Murthy had this idea of balloon experiment for ultraviolet observation, and because I joined him when he was thinking about this idea, I was assigned with starting of this project. So, in principle, if you look at online resources, a amateur balloon experiment seems pretty straightforward and really easy. But it is not so. It's much easier than doing a space mission. But in India, you also have to remember that there's like a lot of permissions you need. Like the rules are kind of ambiguous in the materials you find. So we are extremely thankful for the the Bangalore Airport Authority, as well as Yelahanka Air Force Station, for helping us get through these permissions and stuff. So we had also issues of not properly insulating, overly insulating. So we had I think we had a few unsuccessful launches, but after that we got the hang of how to do experiments, and I guess we have been doing pretty good after that. So our balloons would take us to a height of about 30 kilometers, which would give us some leeway into the shorter spectrum than what you can observe from the ground, and hence a little bit of near ultraviolet. But because of the balloon limitations that we have, the regulations, and also the weight limitations, we couldn't launch large payloads. We could only build payloads up to 6 kg, and most of our experiments were limited till then. And in these points, like Professor Murthy also got into contact with many institutes and groups that were building small satellites, and hence like our group and myself also got involved in a lot of small satellite projects that would lead to possible launches in the future.
So coming to our experiences during PhD in IA, I would say it was definitely a mixed bag, but with mostly positive experiences. As far as work was concerned, I guess we had a lot of academic freedom to sort of find our own path in research. But I think that depends mostly on the supervisor and your group. And I'm also extremely grateful for all the group members that we had as part of the balloon group, or still have in the balloon group. They are quite supportive of each other, and really motivated and helped each other in both technical as well as non-technical aspects of it. And also we're really thankful to Jayant for all the academic freedom that we got, and also he insisted that we work with each other as a group, but at the same time make sure that our work is on par with other people all over the world. And so he pushed us to go to conferences and establish collaborations, and in general talk to people, write proposals with each other, with other people. So, and those things really helped us during our PhD and even afterwards. Also I remember going to the first really international conference, that was an astronomical instrumentation conference by SPIE, and being really blown away by all the work that different people are doing. And those experiences at conferences, I guess really motivate you to strive really hard to do world-class research, but at the same time keep you humble, because you know that there are different people in different parts of the world who do really cool stuff. So that's I guess really important when you're doing a PhD. And like I'm also grateful for that, because a lot of us met our like future employers during conferences. Like I met my current group people during a conference, and I'm like really grateful for Jayan for introducing me to them through email, and also to Ravi for writing so many reference letters whenever I asked. And the other thing, like I feel personally as a woman in IA, is that compared to many other places in the country, IA is like a really good example for women empowerment. Like there are a lot of this women in important places in IA. There has always been, and that doesn't mean like women or female students did never faced any sexism or harassment, but at least, as they say, like you can't be what you can't see. So seeing all these women doing like really important things in like different levels, both science and technical and all other things. So that was like a really good thing. It was a good experience being in IA. So I hope that in future we can also motivate people from different backgrounds into taking up research, and those who do, I hope that we can make them feel encouraged and motivated and supported. And I also feel that there is a lot of room for improvement in our academic culture all over the country, where we like stop patronizing the students and mostly like treat them as colleagues and responsible adults, like they do in most part of the world. That will help a lot in like giving them the opportunity to figure out how to proceed their path in research, and but at the same time provide them the necessary support, guidance, and motivation whenever needed.
Okay, so for me, looking back, PhD is definitely a phase where you learn to do proper research. Like it's a place where you learn stuff and learn from your mistakes. It's also your first experience with working with different groups, working in a group for me, because like I hadn't worked in an industry before. I came just after my college days, so how to write papers. So these were all important for me. Like I learned, so this PhD life for me personally was also made me think about science as general and how it plays an important role outside what you do as well, like for the society per se, like how science plays a role. So I remember that I had carried forward a lot of superstitions from me, from like there were certain things I wouldn't do and I was scared, but like the scientific thought which I started doing in during my PhD helped me get over a lot of those stuff. Like I learned about myself also a lot during this period. It was kind of like an eye-opening experience for me. Like I guess it's for any 20-something person anywhere in India. 20s are the age you learn a lot about yourself. So I was also able to understand a lot of my past mistakes in my professional and personal life, correct them. Professor Jayant has been a great mentor. Like he was always there for us when we needed, but he also gave us the freedom to do. Really had been a great support. Like I don't know, like I would have pestered him for months for a lot of recommendation letters, and he was always happy to give one for us. Like I'm really thankful for him for that. And I also met Ambily during this period. So I would like to say that so before that I have never met a woman with such sense of humor, intelligence, clarity of thought, and conviction, and she has definitely helped me to be a better person in life.
So coming to what we are doing right now, I am part of the Colorado ultraviolet spectroscopy program, and as the name suggests, we are in Colorado and we focus on ultraviolet spectroscopy of objects. So my current project, the project that I'm working on now, is called CUTE, which is the Colorado Ultraviolet Transit Experiment. So it's basically a space telescope. So it's going to be an observatory that's going to orbit the Earth at a height of about 500 kilometers. But when I say telescope or observatory, you might be thinking of like a large telescope and a big dome and a lot of electronic and mechanical structures.
So I actually have, sorry Ambily for, so I actually have a 3D printed 1-to-1 model of the CUTE telescope. So it's the actual size of CUTE. So with the mirror and the instrument and everything. It is not a spacecraft, but it's the actual size. So basically, you can hold it in your hand.
Yeah. So this is the actual size of the telescope that I'm working on right now, and so yeah. So this is the actual size of the telescope. But in addition, it also has all the other support stuff like the communication and the solar panels and the temperature control and monitoring. So all these things are included in a small box about the size of 30 centimeters by 20 centimeters by 10 centimeters. So that is called a CubeSat. So in short, Cube is a 6U CubeSat. Now, what can such a small, tiny CubeSat do? That's really
So so I compliment Ambily in this regard. So I moved to Graz after my PhD to work with Dr. Luca Fossetti, the Space Research Institute here. Space Research Institute is part of the Austrian Academy of Sciences, and our group mostly work on characterizing and observing exoplanets. So exoplanets are planets which orbit around stars other than our sun. So, and our aim of our group is to observe exoplanets and develop software to understand the data from mission like Qt, which will observe exoplanets. So, how we do is that when a planet orbits around a star, like if we are in the proper line of sight, because of the planet orbiting around in front of the star, its light will be dimmed. So, the light dimming of the particular light dimming because of the planet transit will depend upon the size of the planet, and it also depends on the wavelength. So if the planet orbiting the star in this has an atmosphere which has different layers that different wavelengths can penetrate to, you will be able to see the features of the atmosphere while observing this transit. So basically, you are observing a planet during its sunset, and that is what we do in what we call as transmission spectroscopy during a transit. So, and this is what we plan to do with Qt. So we plan to observe planets which are called hot Jupiters, really intelligently named because they are hot and they are the size of Jupiter. So these are planets which are really close to the star, like they are much closer than Mercury, and so they finish their orbit within few days. And because they are really close and they are made of gas, like Jupiter, these are extremely hot planets, and they have materials escaping from their atmosphere. And in observing an ultraviolet wavelength, which Qt will be able to do, we will be able to observe the upper atmosphere of these planets, and we will be able to observe whether materials are escaping from this upper atmosphere, like whether there are metals there, whether there are gases there, what is happening in the upper atmosphere, like whether these we have observed planets which have comet-like tails, materials being thrown out, planets being sucked into the planets, etc. So this is what we plan to do with Qt, and my main aim for Qt has been to develop softwares. Like, so I developed a couple of softwares to simulate the data from Qt, how it will look like. I'm also writing softwares that would reduce the data and analyze the data, and how the data would, like, getting the actual science out of CCD images. I hope we have been helpful to you in our journey as astronomers. Like, this is our journey as astronomers and what we are now. It is true that we both are in two separate sources, but we are working on the same project. That also explains the current status of the science. Like, science is being done more internationally now. Like, people are doing research at different places and coming together to get a bigger picture. It has changed over the century. Like, you would have seen of earlier scientists who used to work individually and they used to find their own things. But now it is changing, and it's a group effort now, like where people from different regions of the world, different cultures, different ideas come together and do something really great. Thank you.
Thank you.
All right. So that was great. And we have some time now for discussions. So it's kind of interesting that both of you are located in different parts of the world, and still you are able to work on the same project. That is your the CUTE, Colorado Ultraviolet Transit Experiment. So it's NASA's CubeSat that will have a low resolution spectrograph to study the transiting exoplanets, right? Now, can you tell a little bit more about this? Like, how is this CubeSat concept different from other big space-borne experiments like HST, JWST, Kepler, or TESS? And also, what is the timeline for its launch, and what kind of science will it do?
Yeah, so I can give a brief introduction about the instrument part. So as you asked, CubeSats are a slightly different way of building space telescopes. So CubeSats in general are like standard building blocks that can be combined to build a larger instrument, a larger satellite. So the basic CubeSat is a 1U CubeSat. So that is 10 centimeter by 10 centimeter by 10 centimeter. And they typically have a standard weight. So a 1U CubeSat is roughly 1.33 kgs. So, and the advantage is that, so it's not, there are multiple components that are available. So if you're building a 6U CubeSat, there are a lot of private companies that will have suitable attitude control systems that can be used for a 6U CubeSat. So you don't, it's easier to pick and choose components that are like suitable for your experiment. And also when it comes to testing, so we are using a particular CubeSat bus, which has certain like attitude control units, certain communication units. So we can always look at people who have used similar, the same bus and the same components, and learn from what they have done on like how to build it, how to test it, those kind of things. So yeah, and also there is the economy of scale. So because there are a larger number of people who are using it, these are like slightly less expensive than building a custom CubeSat, a custom telescope. And coming to advantages for using CubeSats in astronomy, it is that one thing, it is much less expensive than building a custom telescope. And also that because some of these things, like at least the part of the bus, the electronics, the communication, those things are available already. The development time is much lesser. So that's about the instrument, like the advantages of using CubeSats. But the, one thing is that like they cannot obviously not do things as cool as what Hubble or JWST does. So it is our job as scientists to bring up some, like find out some interesting science cases that can be like achieved with the help of a small CubeSat. So for example, in the case of CUTE, it is like, so we showed in the video, there is a transit light curve for the exoplanet. So we basically look at an exoplanet system and see how the light varies depending on when the planet is transiting in front of the star. So that requires a lot of observation time. So ideally, we should be able to look at a transiting system for a long period of time and see the minor variations when it is constant. Like even though we say it is constant, there is like some component of the stellar activity that modifies it, and then how much signal we have while it is transiting, and then after the transit also. So essentially, like the more number of observations you get, the better it is. And those kind of things are difficult to do with a large mission because there are other people who want to use the telescope time. So having a dedicated instrument is a big advantage in these cases. But the trade-off is that we can't look at all the like really faint things. The resolution and the light collecting ability is much less. And coming specifically to CUTE, so yeah, it is a 6U CubeSat. It's going to be launched by NASA in next year, so tentatively September of 2021. And as we said, so it's a 6U CubeSat, so it has a small telescope. It is a 20 centimeter by 10 centimeter telescope. And one like really new thing that we are doing in CUTE is, so you might know that most of the telescope mirrors are circular, or in the case of segmented mirrors, it's going to be hexagonal. But that's not a shape that is suitable for a CubeSat because it's a square or a cubical thing. So we have a rectangular mirror. That's like something that helps in having a much higher collecting area than that could have allowed for a circular mirror. So that's like a really cool thing.
Yeah.
And then
so
I think
to the, I'll just explain the science of Qt as well. So why Qt is able to do is because, so what we plan to observe with Qt is the upper atmosphere of hot Jupiters. So previous observations with Hubble Space Telescope have shown that there is materials escaping from the upper atmosphere of these planets. And these materials escaping is usually hydrogen because these planets are rich in hydrogen. So you usually observe them in Lyman alpha. You also have, say, other metals which are dragged together with hydrogen so that you have other metals escaping as well. So, but the problem is that Hubble Space Telescope is limited in use because you have to share it with other resources and stuff. And for transit, you need multiple transit observations. So Qt will observe in near ultraviolet, so where it will be mainly concentrating on iron and magnesium in upper atmosphere and see how these materials are escaping from the upper atmosphere. So mostly we plan to observe hot Jupiters around bright stars, around less than 10th magnitude stars, greater than 10th magnitude star. So like in the magnitude scale. So these stars which have planets which are short orbit. So most of our planets are like they complete an orbit within few days, so that we can observe maybe close to 10 transit for each target and understand their spectrum. Basically, transmission spectrum. Yeah.
Okay, so there is a question from audience from Neil Kaur, and Neil wants to know, how is the optical instrument different from instruments which are beyond the visible range? Do they work in the same way as visible instrument, or the principle of operation is different?
Okay.
Right?
Yeah.
I think that.
Okay. Yeah. So I'll start. Then Ambily can add if I miss something. So
right. Yeah, just briefly.
Yeah. It is true that the instruments are slightly different in different wavelengths. Like for example, in ultraviolet is similar to that in optical, like because only thing is that you will have to have materials and materials that work in ultraviolet. So you would have mirror coatings that would reflect in ultraviolet. Your lenses would be of materials that would have proper refractive index and transmission in ultraviolet. So that is one thing. The detectors are slightly different because your normal CCDs, because they are silicon based and they're because of their energy gap, they wouldn't work in wavelengths about 200 nanometers. So if you need to observe below that, you need something to convert these photons into electrons or photons in other wavelengths. So there are things called like you may know about photomultiplier tubes, or there are micro channel plates. There are different things by which the detectors are slightly different. In the same case in infrared, for some wavelengths you can do with silicon detectors, but if you go further, you would need detectors which are made of certain different material. You would need, as you go further, you would need different materials for focusing your optics. For example, radio, you have dish antennas and stuff instead of optical telescopes. So for example, the dish antennas that you have at your homes for receiving radio signals from DTH signals, etc., are similar. So you would have things similar to that. X-rays, because similar to how our X-ray in hospitals work, you would have things which are in grazing optics, and you have sheets which are, for example, Chandra telescope has sheets which are like hold together, and the rays actually bend through that. So it's slightly different. It's the same with gamma rays. If I miss some, so it depends. The instruments and the method how you do stuff varies with wavelength. So, Ambily, have anything to add that I missed?
Yeah, it's mostly that. Like it's mostly the at least for a broad set of wavelengths from the far ultraviolet to somewhere in the infrared. It's somewhat similar, like it's similar instruments. It's just the coatings that are different and the type of detectors, and like at least in the case of Qt in the NUV. So we have a CCD detector, but since it is in the ultraviolet, it requires cooling and then like some optimization on the chip to make them sensitive to the ultraviolet. But yeah, when it comes to radio or like really short wavelengths, it's a completely different.
Right. Okay, so interestingly, in your video, you both spoke and also acknowledged the influence of your parents in rousing your early interest in science. You also grew up reading popular science magazines in Malayalam, and it seems People's Science Movement in Kerala, especially KSSP, has played a key role in promoting scientific temper at grassroots levels. So there is a dire need of popular science literature in other languages that we all agree. And I think it's also important to keep this tradition going. And I feel that new generation must benefit from your experience and knowledge. And one way to motivate youngsters is to regularly write interesting science article for local science magazine like Eureka. But other than that, what do you think we can collectively do to address the general lack of science and scientific temper in our society? You have your thoughts on those? If you could briefly share.
Ambily, why don't you go ahead to start? I guess.
Yeah,
Uh,
anyone?
yeah, I guess like Eureka was a great influence for both of us, and I'm sure like many other
Uh-huh.
like students who grew up in our age. And one thing with the people science movement in Kerala and like magazines like Eureka was that it was like very accessible to students. Like it's not it like okay, you can have science literature in languages like local languages, but it's also important that you make sure that they reach students. So like Sreejith studied in a like a CBSE school. I studied in a private uh, state syllabus school, and our parents worked in like government LP schools, government schools. But like all of us could have access to Eureka. Like so, that was a great thing in that regard. So like be it villages or be it small towns or larger cities, it was like ubiquitous everywhere. So that was a good thing. And the other thing was that they were all written in a language like that is like understandable for children, and it was as if like you're having a conversation with a friendly teacher or a friendly
Mhm.
uncle or so that was a, so that's what attracted me as a child to read them. It was not like a scientist is telling you things. It's more
Yeah,
like
yeah. But
a
Ambly,
friendly
that
person.
time is gone. So what will you do?
uh, I think as scientists we have a responsibility to like write
Mhm.
actually like yeah, write in our local languages and like make sure that people read it. That's like really important. Like how we do outreach activities in IA, where you go to
Right.
different schools in different parts of the parts of Bangalore or Karnataka as such and talk to them. And so yeah, that is really important. And I think like we have a duty to continue like the like
Right.
students in IA or like even after you like, leave IA, it's like really important. And especially this time of pandemic has been in that way a different experience because like there is more opportunity to do like Zoom like sessions where you can interact with scientists.
Right.
So I think it's upon us to utilize this opportunity and
Yeah.
do that. I think
Sreejith, you want to add quickly something?
Yeah. I'll just add quickly maybe a couple of things. Like one is that it's definitely true that in this day and age, where there's like enough false information in the social media, that we need to actually put forward the ideas of scientific temper and scientific knowledge, and why science happens in certain way and why it is important. So if like I know of stuff happening in Kerala and in Malayalam where there's like a lot of YouTube, there's a lot of communities in YouTube which actively promote science through social media and other methods, where they have usually talks regularly, or they
Mhm.
have discussions and stuff. I don't know of other regional languages in India, but it would be a good idea to have in maybe all of the regional. I think this happens in Tamil as well, but I don't know if other regional languages whether something like that is happening. But I guess it's a really good idea for like scientists should join this effort. But one thing which we like when scientists when they communicate with others is like we should be able to communicate with students and general public in a way that they easily understand, like rather than using jargons and words that which we are comfortable with, because that would make it easier to for like relating to their daily lives, relating to things that people experience in their days lives. That would be really helpful.
Okay, before we go to the next question from audience, I had some time back, I had requested Professor Jayant Murthy, who was your supervisor at IIA, to talk about balloon program and also his UV group. So here is what he has to say. So I'll just play that video. It's a very short video, but let us just hear him say.
Sreejith was the first of the MTech students to join me, and really the leader of the group in many ways. When he joined, we had nothing. We were starting from scratch, and so it was his responsibility to build up the lab, get all the tools that we needed, buy the balloons, the parachutes, and whatever else we needed. So he really had the most difficult job in a sense. After him came Joyce and Mayresh, and then Ambily and Nirmal. And by that time, we already had a good working setup. We knew what to do. Everything was getting streamlined, and so they reaped the benefit of Sreejith's work. Now, what this program was really we started by developing small payloads for balloon flights. And then we thought that eventually we would work up to space missions and building missions that would go up into space. And that is pretty much the way it worked. Unfortunately, none of the students who started managed to get an actual space flight. You know, these things take time. And so they all built payloads that were ready to go into space, but are still sitting in our lab. Now, the important thing about all of them is that they all managed to do basically everything on the payload development. They started with the initial science problem, and then they developed the payload design. They bought whatever had to be bought, and in this I'm very grateful to DST for providing the funds for this, and the Institute, of course, and IIA, of course. And then after that, they had to put everything together. They had to calibrate it, align it, and so it gave them experience in every aspect of space mission development. And this, I think, has served them well in the jobs that they're now doing. Every single one of them is working on a mission that has been accepted and that will fly in the next few years. So I think it's worked out well for me, and it's worked out well for them. It's been a good program, and most of it is because of the enthusiasm of the students. Now, as I said, Sreejith was the first of these, and he was always the most enthusiastic, and in some ways maybe overly enthusiastic. He was so enthusiastic about every single project that sometimes it was difficult for him to focus on any single project. Ambily was different. She came in, she was very quiet when she came, hardly spoke at all, but always very focused on what she was doing, learned whatever she had to do, and by the end of her graduate student career, she was speaking up and speaking her mind, telling me what she wanted to do, not what I wanted her to do. So I think both of them grew quite a lot in their time, which is as it should be, and they're now well suited to take leadership roles in the projects they're working on. So as far as advice for them, I really don't have much. It's a very different field than when I started. And it's always difficult for couples because you have to balance where you are and your personal life, and so I'm sure they will do well, and I wish them all the best for the future.
Okay, yeah, that's nice. Thanks, Jayant. I think we have a question from audience. So quickly, if you can answer, because we are running behind the time. The question is from Sumukha CS, and so how do the exoplanets are confirmed? Is and how do we say, or how do we know their composition and size? So quickly, if you can tell that.
Okay.
I think you have already explained how the exoplanets are detected, but how do we know their composition or size, whether they are rocky or gaseous planet?
Okay, so there are many things. So as I mentioned earlier, one of the methods is transit method. So you have multiple transits and you observe and see whether there is dimming of light. So with transit methods, you will be able to measure the size of the planets, because the dimming in the light is directly proportional to the size of the planets. And if you know the radius of the star, the light curve, the depth of the light curve would correspond to the ratio between the radiuses.
Right.
So that's how you find the radius, the size of the planets. That's a main method. But you need mass information and usually use radial velocity measurements. So you see how you measure the radial velocity variations of this planet when it is moving around the star. And with this measurement, you have the mass. If you have the mass and the radius, you can calculate the density. And with density, you would be able to tell because density will give you an idea of what the material would be, whether it is made of gas, whether it is water, whether it's rocky, because as you know, different materials have different density, and that will give you an idea. And composition, you use, like as of now, our main method of you finding the composition is basically the atmosphere composition. We use transmission spectroscopy. That is, when a planet passes in front of the starlight passes through the atmosphere of the planet. And while observing this and comparing it with the stellar spectrum before the transit and after transit and during transit, in different wavelengths, you will be able to say at what level of atmosphere you have what components. So whether there is like hydrogen, helium, sodium, metal like iron, magnesium, or water, carbon dioxide, all these things.
Yeah, great. I think that answers Sumukha's question. And the last question is just for the benefit of our own students. So can you also talk about a little bit about your postdoctoral experience abroad and how it is different or similar to your PhD experience in IIA? Let us say in terms of motivation, work environment, exposure, peer support, and approach to research and development in general. So quickly, because this question I have been asking from all our previous speakers, so I think it makes sense to put it to you as well.
Ambily, go ahead.
Oh, okay. Yeah, a postdoctoral experience has been like little different in the sense, like as a postdoc, like you're supposed to be more in charge of the work that you do, like define your own problems and work on it on your own. But it's also similar in the sense that because it's an instrumentation project, it's a large group here, and even in IIA we had a experience of working in a larger group. But it's a different culture and a different set of people, so adjusting to it takes a little bit of time. But like just to observe in the difference, one thing is that here people are supposed to be like more responsible, like even as students, like PhD students or undergraduate students, they're more considered as peers or colleagues. So they're like given a task and they're expected to finish it. So it's like a more independent thing that like even in IA, like from our experience, like we had a similar work, but like in general, I think people are like more the focus is more on like finishing tasks than.
I see.
Yeah. Like maybe either in many groups in India, it's more like a student-teacher relationship even when you get into PhD. But what I have noticed here is that it's more colleagues rather than like it's that is still there, that it's a supervisor and you're a PhD student, but it's more like you both are working towards the same goal or same principle. So another thing I noticed, the main difference was that the work, like because I'm in Austria and they have a strict European work-life balance thing, so they usually work from a particular time, and when they work, they actually concentrate on work, which was like really different from what we have in India, like where. So I used to go on weekends as well to the institute to work, but sometimes like you spend long hours in the institute, but it doesn't mean that you put full effort on working. But here, when people work on something, they are extremely focused, and when they are free, they are extremely detached from work, and they do whatever stuff they want to do. So like I think I had the discussion with Ravi earlier about like how students still address their like everyone who's like who are faculty in the institutes as sir and madam and stuff. Like I still do that sometimes, but it's like here. But you always like I remember that the current supervisor I have here. The moment I was accepted for this job, the next thing he said me was that call me by my first name now onwards. Don't call me doctor, professor, sir, or anything. Just call me by my first name. And so that actually changes because like, see, once you start calling someone by name, you are like, you feel that you can discuss much more with them, like because there's no that difference between a student and faculty. So that is something which we can improve in IEA, like which we can actually force, and we can force the students not to call us sirs or madams anymore, and that would maybe change some things as well.
Yeah, I think it's changing slowly. So hopefully it will.
Yeah, it's definitely changing.
Yes. So we do not have any more time to take questions from audience, and because we have already reached the end of our allotted time. So I want to thank you both for giving your valuable time and sharing your fascinating science stories. Thank you, and wish you all the best for future.
Yeah. Thanks,
So,
Ravi.
Thank you, Ravi. Thank you first.
Yes. So we will continue this conversation in our next episode. You can subscribe to our YouTube channel to get regular updates about our outreach activities. But before I end this program, I have a small announcement to make about this year's India International Science Festival. So I will just share the advertisement. Okay. So India International Science Festival is an annual event that was launched in 2015 with a goal to promote science and technology that would help India become a developed nation. The festival aims to engage the general public and students in celebrating the joy of science and to show how science, technology, engineering, and mathematics can be used to solve many pressing problems of the society. This program is jointly conducted by the Ministry of Science and Technology, Ministry of Earth Sciences, and Ministry of Health and Family Welfare. This year, the theme of the festival is Science for Self-Reliant India and Global Welfare. Due to ongoing pandemic, this year the IISF event will be held completely online from 22nd to 25th December. So you can visit the IISF website, scienceindiafest.org, for registration. So my own take on this is that, yes, big science festivals are important, but more important is the message that comes from these events. Last time when I attended such festival in IIT Delhi, there were several exhibitions put up by many organizations, research organizations, showcasing their achievements in science and technology. But just opposite to ISRO exhibition, there was a stall put up by a religious organization, which was drawing a bigger crowd. The man was making all kind of unscientific and misleading claims. So I couldn't help noticing a shocking and confused look on the face of high school students who were listening to him for quite some time. I think we cannot afford to raise a confused generation of young students and still hope to reap the benefit of modern science. Conflating science with obscurantist and pseudoscientific idea has to stop, and the change must begin from the top. So with that, I thank you for joining and have a nice weekend.